Hello, Calculus 2 class. Today we start the chapter on differential equations, and it's kind of timely because the first section of your chapter deals with epidemics. So let's look at a logistic model. It's called the logistic model, and it's all good stuff. It'll help you when you're reading the newspaper. Huh, what's this axe doing over here? Get that out of the picture. I don't want to make it seem like I'm panicking or anything, because everything's great. Everything's just fine. You know, everything you read on the news is telling you to panic, but don't panic. Everything's just fine. Let's see what the numbers look like. We've got some New York City numbers. This is just from the New York Times. I don't know if you trust the New York Times. I don't trust anybody out there. If they're going to talk about math, they're usually wrong. But this is their number infected. On March 25th, they said they had 20,000. Now, this is actually not a bad source of data because New York City is testing more than almost any other place. So they're testing a lot of people. I'm going to use 8 million as the population of New York because my variable p is going to be a proportion. So that means that p is between 0 and 1. You know, it's 20% or 5% or whatever. So you see these numbers when you have 20,000 out of 8 million, the proportion is very small. And then you have 38,000 out of 8 million. And then they say, as of today, as of this afternoon, close to 80,000 have tested positive. So it's just the people who have tested positive. It's not the deaths. It's just the tested positive thing. All right, so we've got some data, and here's the math behind it. So this is section 1. A differential equation uses a derivative as a variable. So if you look at it, it's an equation. K is the hotness of the epidemic. It's the contagiousness of it. This is also the same model you use for a rumor, because the speed at which the proportion changes is equal to how hot the infection is, or how hot the rumor is, times the number of people who aren't infected, times the proportion of people, times the proportion of people who are infected. So one thing you can see right away with this is the following. If you have, this is the p-axis, this is the t-axis. When p is equal to 1, that means 100% of the people are infected, or 100% of the people know the rumor. You stay at 100%. So that's actually a solution. So, that's right. So we have a differential equation, and the solution is a function called p of t. So instead of getting the answer is 5 or the answer is 12, now the solution is a function. Well, here's a solution, p equals 1, which if it was an epidemic, that would be bad news. But like a rumor, a very hot rumor, like did you hear that that McDaniel's just going to give everybody A's for the rest of his life? That's a hot rumor. It would spread like wildfire. Anyway, so very quickly everybody would know the thing. So that's what the solution would be. P equals 100%. P equals 1. But here's what actually happens. You start with A. At time 0, you have some small amount, and your solutions take this kind of shape. And this is called a logistic curve. And this kind of curve is how a lot of stuff grows. Anytime there's a limit on things. So for instance, we actually did this once. I did this with some high school kids. We got some data for average height of adult males in industrial countries over the last 150 years. And we were getting points that fit like that. And you can do a regression equation on your calculator. It gives you the curve. And we got, a shape like this that said that the average adult male height in 150 years would be 6'4", which seems a little high, but it is true though. The average adult male height has been increasing, but it can't go up forever. You can't have populations using just plain e to the rt curves, because there's unlimited growth. Like if you use a purely exponential model like e to the rt, p e to the rt model for your x, and some news people do this. They're slobs. Because you can't use it for long term, because this is unimpeded growth. Even in a city like 8 million people in New York City, how many people can get infected? 8 million. After that, there's nobody left to get infected. So, you can't use something that has, well, you know what, in a couple of months, there's going to be 80 million people in New York infected. No, you can't have 80 million people in New York. There's only 8 million to start with. So these kind of models are terrible. So this is more like it. And what's cool is, we get this kind of curve when we solve this differential equation. So this is called a phase plane, where you draw solutions in. Oh, and here's another one. If nobody's ever infected, p equals 0, that's a solution as well. So that would be like smallpox. There's basically nobody with smallpox has been eradicated from the planet. So the proportion of people on the planet with smallpox is 0, and the number of people with smallpox tomorrow is going to be 0. Unless some idiot goes to the CDC and steals some smallpox out of the cooler and just throws it out into the air. Then people get smallpox again. But anyway, so you can draw what the solutions look like because this is a derivative. You can have little tangents. You can take a tangent at various points using this formula, but you need a specific k. Well, we don't have that specific k, but now we're going to skip to the third section and show you how to solve this. This is actually a separable differential equation, and it's because of Leibniz's cool notation. I'm going to treat this as if it's a fraction, and I can rewrite this as dp over 1 minus p times p, and that equals k dt. It looks like I multiplied by dt and divided by all this p stuff over there. And now this looks really funny because I've got a dp and I've got a dt, and they don't look good all by themselves because they need an integral sign in front. So we write that integral sign in front. Now this is a partial fractions integral, and I did the work. It comes out to be the integral of dp over 1 minus p plus the integral of dp over p. In other words, the capital A and the capital B from the partial fractions both came out to be 1. Works out nice. This side, I get kt plus c. That integration constant, that arbitrary constant, ends up being crucial. Super important. Don't lose it. You got to have it. So now, this side, if I can do both of these integrals, I'm going to skip a little bit because I just want to get to the end. Remember, we're going to have a natural log for each, but this guy requires an adjustment because the derivative of the downstairs is -1, not just 1. The derivative of this downstairs is just 1. So I end up with the natural log, and you can do this yourself, of p over 1 minus p. Now there's supposed to be absolute values, but remember p is stuck between 0 and 1. So that means that p is positive and 1 minus p is positive. So I don't need absolute values on there. And this comes out to be equal to, it's still equal to the kt plus c, but you can see where this is going to go. I'm going to raise both of these as powers on e. So the e and the natural log kill each other off, and I have p over 1 minus p equals e to the kt plus c. Now this you got to be able to handle. That's the same as e to the kt times e to the c. And e to the c, it's e to an arbitrary constant, so it's an arbitrary constant. We usually write it as an a, e to the kt. So we have p over 1 minus p equals that. Now, this is a good time to use our data. So I did the numbers ahead of time. The proportions that we get for these 3 numbers up there, the 20,000, the proportion comes out to be 0.0025. For the 38,000, 0.00475. And the 80,000, obviously 0.0. Is it 0.01? Yeah, 0.01 for the 80,000. So the 80,000, they're reaching 1% of the population is infected, which sounds small, but it's 8 million people, so 1% is 80,000. It's a big amount. So there's our proportions. You can pop the 0.0025 in, and what I would do is I would call 325, March 25th, I'd call that times 0, because then you put in a 0 for that t right there. E to the 0 is 1, and I get a equals, I did the math, if you put in 0 for t equals 0, you get a equals, and this thing here is the 0.025 over 1 minus 0.0025, which comes out to be, I've got the number here, 0.00251. Almost 0.0025, which makes sense because there's not that much difference between these. Well, anyway, so you get this for the A. Now, I'm going to erase because I need the space. So that tells me that P over 1 minus P is 0.00251 e to the kt. And now I still have another piece of data, the 0.00475. It's 5 days later. So I can put t equals 5 right there, and p equals 0.00475, and that gives me the k. The k turns out to be kind of scary. I'll leave you to solve, but the k is equal to, I got k equals 0.1285. Let me just give you an idea how scary that is. When you do the PERT model for interest compounded continuously, that would be 12.85, basically 13% interest. 13% interest, you got rapid growth on your investment. This is rapid growth. Let me tell you another thing. If that was 0.02, it would be officially wet your pants time, lock the doors, and quarantine everybody, according to the CDC and the World Health Organization. But it's 0.12. Oh, that's big growth. That means the virus is spreading very quickly. So anyway, so this gives us our model of p over 1 minus p equals 0.00251 e to the 0.1285. Now here's what I did for you. Cross multiply. You can cross multiply this. You can cross multiply and solve for p. You actually can. I already did it. So I get p equals, this is the p of t. I get p equals 0.00251 e to the 0.1285 t over 1 plus 0.00251 e to the 0.1285 t. So that's my p of t. That's my solution. I got a closed solution. Now one of the things I can do is I can check to see when t equals 6, do I get 1%? Remember this came out to be 0.01? And when I did t equals 6 on my own, t equals 6, this came out to be 0.00487. So that's a much smaller number than if the number today was reported correctly in the New York Times, that it's close to 80,000 tested positive as of today. There's two things going on. One, quarantine doesn't seem to be working very well. This thing's growing the way it would if it was just a regular old epidemic. Or two, remember how they're testing more people? What they're finding is they're testing people who already have it, and they may have had it for a while. So we aren't getting a real reading on how many new cases there are. We're maybe finding a bunch of old cases. So it's not the best. It's not the best. It's not like we're out in front of this thing and we're finding new people and we're keeping track of them. We're probably finding people that have had it for a while, along with people that have newly been infected. But anyway, these two numbers don't match very well, which means that the data that we've got isn't working as a logistic model very well. Something's not working so hot. But that's just the math part. And that's why I don't believe anybody's math on this, because it's so complicated. But anyway, you can graph this, and I graphed this on my calculator. Let me show you real quick. I've got the graph of this thing. And there it is. Let's see if we can get you guys to see it. Hang on. Oh, I hit graph. Show graph. Come on. Come on. Come on. You see it, right? That's the shape we had from just drawing it by the phase plane. We got the right shape. Complicated looking animal, but all the logistics have this kind of structure. So that's how you solve a separable. You separate the pieces and do integrals of both sides. So that should enable you to do problems from section 3. And section 1, you can try some problems from there, but they're just asking you, basic differential equations problems. So try some separables from section 3. Section 2 is a computer problem. We're not going to be going to the computer lab, so skip it. All right. Don't panic. Stay tough. I'm looking forward to seeing you again someday.